Hello all, I am Shatabdi Acharya from Vedang Institute of Technology, and today in this module we will be taking up a new chapter which is hydrocarbons, right? So before proceeding on to hydrocarbons, let us learn something about our friend for the entire chapter, right? In this entire chapter we will be studying about one common element which is carbon. Okay, so before going into the chapter, let's make some friendship with carbon. Let's know what carbon is exactly, right? Okay, so carbon, this symbol stands for carbon, represented as C. So carbon is the first element of group 14 in the periodic table and it has atomic number 6, right? So if we try to write the electronic configuration of carbon, it is 1s2, 2s2, 2p2, and as the last electron goes into the p subshell of this element, of this particular element, therefore this element belongs to the p block. Okay, so this element belongs to the p block of the periodic table. You know, periodic table is divided into 4 blocks depending upon to which orbital the last electron goes. We have s orbital, p orbital, d orbital and f orbital. S orbital, as the name suggests, the last electron might be going into the s subshell. And for s, remember in atomic structure we have understood s is having only one subshell. So in a particular subshell or a particular orbital we can only fill 2 electrons, that boxes. So in this box we can fill 2 electrons. Therefore there are 2 groups for s orbital or s subshell. Therefore only 2 groups are placed under s block elements. Next is p block elements. For p we were drawing 3 boxes of this kind, right? Basically 3 orbitals in the 3 axes px, py and pz. So for p, filling up these electrons, like these orbitals, we need 6 electrons and therefore we have 6 groups under p block. Similarly for d we are having 10 groups and for f 14 we are having 14 groups. Now carbon is our member of the p block. Okay, there are 6 groups in the p block and carbon is the member of the p block, that is the 14th group of the p block. Okay, so the electronic configuration for carbon is 1s2, 2s2, 2p2. So the first point is what kind of bond carbon will form, right? So what we learnt before is if a particular atom is having 1, 2 and 3 electrons in its outermost shell, then that atom would prefer basically to lose these electrons, right? That atom loses these 1, 2 and 3 electrons respectively to develop a charge of +1, +2 and +3 over it. Okay, and this characteristic was typically shown by metals. Now the elements having 5, 6 and 7 electrons in their outermost shell, what they prefer to do is they like to gain electrons from their surrounding to complete their octet. And why this loss and gain of electron was happening? Basically to fulfill the stable octet configuration of that particular element. Okay, so every element, in order to be stable, in order to be in a lower energy state, they had to have 8 electrons in the outermost shell, and that's why to attain that stable octet configuration they were supposed to gain or lose electrons among themselves. Now if we observe carbon, it has 4 electrons in the valence shell. So here we are talking about the cases of 1, 2, 3, 5, 6, 7, but we skipped 4, right? So what the element with atomic number 4 will do? It has equal 50-50 probability. It can either lose these 4 electrons or it can gain 4 electrons somehow. But for extracting 4 electrons from a metal, we require very high ionization enthalpy, right? We require very large amount of energy. the energy demand of the atom increases when we try to go beyond the third electron. Therefore, extracting these 4 electrons from the orbital of carbon is very difficult. Carbon will not give its 4 electrons to any other metal, right? Now, okay, then we can make terms with carbon and we'll say somehow we will give you 4 electrons, gain that 4 electrons also. No, carbon can't do that also, because when carbon starts gaining 4 electron, we know electron gain enthalpy. Whenever an atom gains electron, they liberate energy to the surrounding. So when these 4 electrons will be gained, a very huge amount of energy will be released to the surrounding, and that is not feasible at all. Therefore, carbon can neither gain electron nor lose electron. So what will carbon do? Then we came into an amicable solution where carbon shares its electron. How? With other deficient atoms. For example, if I am saying carbon and hydrogen, for example, let us take this. Carbon is having 1 unpaired electron, basically 4 unpaired electrons within its outermost shell, and hydrogen is also having a 1 single unpaired electron. Now carbon also needs to form a bond with hydrogen, because carbon is also in need of electrons, and similarly hydrogen having 1 particular electron, 1 unpaired electron, is also in a need of electron. So what they will do, they will make friendship among themselves, they will share these electrons, and these electrons are now belonging to both carbon and hydrogen. These electrons will be placed in the middle. These 2 electron pairs, which we call electron clouds, because electrons are 3-dimensional entities. They are present in a 3D space around the nucleus, as given to us by Schrödinger's wave equation, if you might have remembered from atomic structure. Then we call it electron density. Now this electron density is shared equally by carbon and hydrogen. Carbon cannot say both these electrons are mine, neither can hydrogen do the same. These pair of electrons belong to both carbon as well as hydrogen. Therefore, similar sharing carbon can do 4 times, because it is having 4 unpaired electrons in its outermost orbital. So basically carbon can form 4 covalent bonds, right? Therefore, what we came to the conclusion is carbon can neither gain electron nor lose electron. What carbon can do is share electron. And how many electrons can carbon share? 4 electrons. And you know we have a prefix tetra associated with the number 4. So as carbon can share 4 electrons, and we know sharing loss or gain, an element develops a charge over it, which we call as the valency of that element. Now as carbon can share 4 electrons, therefore carbon is said to be tetravalent, means it shows a valency of 4, neither plus nor minus, it shows the valency of 4, therefore it's called as a tetravalent atom. Okay, so we knew something about carbon, like carbon is an element which is belonging to the p block of the periodic table. It has atomic number 14, that means it has it has atomic number 6, that means it has 6 electrons and 6 protons, and 6 electrons are distributed in the electronic configuration 1s2, 2s2, 2p2. Now due to the presence of, okay, which will be its valence electron, if I am saying 2s2, 2s2, 1s2, 2s2, 2p2, then which one will be its valence electron? Obviously the valence shell will be the highest quantum number, highest principal quantum number state, so which is the 2s2, 2p2. Now in its valence shell the carbon is having 4 pair of electrons or 4 electrons, and it needs to have another 4 electrons in order to form or in order to satisfy its stable octet configuration. So excuse me. So what carbon will do basically? Carbon prefers sharing of electrons with other atoms, and it will share 4 electrons. Therefore, carbon is said to be tetravalent. I hope I'm clear with this point. Okay, now we'll move on to the next point, which is self combination. Now what does self combination means? Okay, Now carbon has, we know, carbon has 4 unpaired electrons in its outermost orbit or outermost shell. Now, in order to complete its octet, it needs to share pair of or 4 electrons with some other atoms. Now, if carbon has to share electrons only, why it will go for other atoms when it can also share with another carbon atom of its own category, with its own brother, right? Carbon will say, so carbon will say, I am having 4 unpaired electrons. So one thing I can do, I can combine with another carbon atom. It's also having 4 unpaired electrons. Then we both can share one pair. At least we will get one pair of self-linked or self-bonded electron pairs where I can help my own brother. So here carbon will share its one electron pair with another carbon atom. Now this carbon atom can also do the same with another carbon atom here. 4 electrons are there. So basically they can form bond among themselves. Now this phenomenon continues over a long chain. Okay. And why this continues over long chain? Because if you see, the size of individual carbon atom is very small. Okay, the size of an individual carbon atom is very small. As a result, its outermost shell is closer to the nucleus. Therefore, the nucleus has a strong hold on its outermost shell, as a result of which the nucleus of this particular carbon will hold this electron pair very strongly, and so will the nucleus of this second carbon atom. This phenomenon continues over a long chain. Therefore, the chain they form is comparatively stabler and stronger. So, carbon has the tendency to link n number of carbon atoms to itself. It can form long chains of compounds. It can link with itself to form a long range of compounds with this self-linking property. Now, this self-linking property is known as catenation. Due to this phenomenon of catenation, carbon has a tendency to form variety of organic compounds. Large number of organic compounds can be formed by this carbon because of this particular property called as catenation. Now, the elements belonging to this group, we knew that in the periodic table, elements of the particular group, they show similar properties. So, gradually what happens, this self-linking tendency decreases down the group. Why? Because as we go down the group, if we observe this particular group, we have carbon, silicon, germanium, okay, stannous, lead, Sn, Pb. We have these elements. So as we go down, gradually what happens, the size of the atom increases. As the size of the atom increases, distance from its nucleus also increases. As a result of which the nuclear hold on the outermost shell decreases. Therefore, this self-linking property also decreases. Therefore, we can say the property of catenation, yes, carbon shows a very strong property of catenation, but silicon also to some extent shows this property, but it's very weak, like it is comparatively weaker than carbon, and as we move downwards, this tendency decreases, almost fades away. Okay, so this self combination property is called as catenation. Next is occurrence of carbon. How can we find this Mr. Carbon? Okay, carbon we can find in two ways. One is in the free state, second in the combined state. How in the free state? We are having various elements like coal, graphite, diamond we are getting. In those states basically carbon is present in the free state as a carbon only, carbon atom, element, okay. But in combined state, you must have observed carbon dioxide, the very famous gas, carbon dioxide, and as certain carbonates also. Okay, like this carbon atom is present in a combined state as well as in a free state also. Now, we will understand a very important thing. What is allotropes? Okay, allotropes of carbon. Basically, the allotrope of something is various physical forms of one particular element. Okay, so allotropes are various physical forms of an element. Let us write various physical forms of an element. Okay, if one particular element can exist in a variety of forms physically, no chemical difference in between them. If we go to the grassroots level, it is the same element, but the form or the arrangement of atoms in them are different. Okay, so that particular term we use for the various physical forms of that element are called as allotropes. And if we see our carbon, we have mostly 3 allotropes of carbon, out of which 2 you are well aware of, but the third one is comparatively newer to us. So what are the 3 forms? One is diamond, we all know. Second, graphite. Lastly, we have heard about this person in our previous lectures of chemical bonding, like we started our chemical bonding from this, and that person is Buckminster Fullerton. Buckminster Fullerton. Okay, so carbon basically exists in in these 3 forms, or in these 3 allotropic forms: diamond, graphite and Buckminster Fullerton. So you all were aware of diamond and graphite, like in some part of your life, here and there you might have heard about these, right? Diamond and graphite. So what are diamond? What is diamond? Diamond is the hardest chemical, hardest naturally obtainable element, you can say. Diamond is the hardest naturally occurring element. Okay, and diamond is known for its very high shiny surface, right? And being hard, diamond is used for various cutting, welding and these all works. Diamond is used, and basically we are also using diamond in our ornaments. Okay, so how do we know that diamond is made up of carbon? See, diamond is a very hard metal. Okay, we cannot, it does not undergo any chemical reaction, but had it been undergoing any, then if we heat diamond under at a very high temperature, it burns, or it burns with oxygen to give rise to carbon dioxide, and if you pass this on lime water, it turns milky. So with that we confirm that diamond is purely made up of carbon. Okay, if suppose we are heating diamond, then now next comes graphite. So if we compare graphite with diamond, then comparatively this is softer one as compared to diamond, right? Graphite we are using in our pencil needles, pencil nibs. It breaks easily because it is very soft as compared to diamond. So this graphite is a very soft form or softer allotropic form of carbon. And what is the basic difference between these diamond and graphite? First thing is, physically you will observe the color. Diamond is very shiny, graphite is a dark and dull, comparatively dark and dull form of carbon. This is soft, this is very hard. Diamond is very hard, graphite is very soft comparatively. And the next thing is, diamond is a poor conductor of electricity, but graphite is a very good conductor. Very good conductor of heat and electricity. But why is this? Both are made up of carbon. One is very poor conductor of heat and electricity, another is a good conductor of electricity. Why? The answer lies in their structure. Even the reason for their hardness also lies in their structure. So let us see. This is the structure of diamond. This is a rough diagram or the rough sketch of how diamond looks like. This completely somehow appears to be the diamond shape of that actual diamond. So what happens here is, these circles, these are carbon atoms. Okay, these are carbon atoms. And see, one carbon atom here is linked to 4 different carbon atoms in a tetrahedral manner. So in diamond, you remember, the carbon atoms are linked to each other in a tetrahedral manner. Got it? So here one carbon atom is linked to 4 other carbon atoms. Basically this structure continues, this structure goes on continuing. So what we observe, carbon basically has the tendency to form 4 bonds, and here all the 4 bonds are satisfied in linking to 4 other carbon atoms. So is there any free electrons available in diamond? Obviously no, because carbon has only 4 unpaired electrons, and all the 4 unpaired electrons are used up in bonding with other 4 carbon atoms. And we know electrons are the key elements for the transfer of electricity. So as there are no free electrons available in case of diamond, therefore diamond is a very poor conductor of electricity. So what's the reason we get here? Unavailability of free electrons. Okay, basically electrons are the carrier of electricity. As the carriers are only not available, how will electricity be conducted in that medium, right? Obviously no. And here see, carbon atoms are very closely packed, very compact structure they are having comparatively. So as a result of what happens? Diamond is very hard. So the entire physical and chemical property of these like allotropic forms, they do not have different chemical properties though. The entire physical property lies in their structure. Now if we observe the case of graphite, in case of graphite what we see, each carbon atom is bonded to 3 other carbon atoms. Okay, here there will be 1 carbon atom, this chain will be continuing. So each carbon here, they will be bonding, they will be bonding. Okay, we haven't shown there, we are only taking, I just took a section of graphite, this is a sectional diagram I'm trying to represent. So here what happens, each carbon atom is bonded to 3 other carbon atoms, and carbon has 4 electrons. So basically what happens, and again the most important thing here to notice, this bond, the bond formed between 2 different sheets, 2 different layers, what happens, this bond is basically van der Waals force. Van der Waals interaction. And we know this is a very weak force of interaction between any 2 molecules. So as these are, like the distance between them is large, therefore the only force of attraction existing between them is this van der Waals force of attraction, and as a result of which they exist as a sheet like manner. Due to this weak bond between them, these sheets can basically slide over each other, and due to this graphite is comparatively softer. Now due to the availability, like 1 carbon is bonded to 3 other carbon atoms, therefore 1 pair of electron is free in case of graphite. So as a result of this phenomenon, what happens, as when we pass current or electricity, we have our carriers available over here. Therefore those carriers take up our electricity and conduct it in the entire medium. Therefore graphite is a good conductor of heat and electricity due to the availability of good conductor due to the availability of free electrons. Okay, now what about our last allotropic form, Buckminster fullerene? So Buckminster fullerene was a basically carbon 60 compound. Buckminster fullerene was a carbon 60 compound, and it was named after Buckminster Fuller, who was an architect, designing the dome-shaped buildings of various monuments. Okay, he was basically designing dome-shaped monuments, and as the shape of this Buckminster Fullerene is a football shape, where we have 20 hexagons and 12 pentagons linked to each other. Okay, the structure is a very complex structure, but it's a tiny structure. It's still complex. It is made up of 20 hexagons and 12 pentagons. It is a carbon-60 compound, and it is in the shape of football. Okay, and it is also a very dark colored compound. And it is, as it is a very newer discovered compound, therefore very less is known about its property. So you just have to remember is carbon-60 is called as Buckminster Fullerene, and it is dark colored. Its shape is football shaped, and there are 20 hexagons and 12 pentagons linked together to give that football like three-dimensional structure. So in this video we have learned a lot of things about our carbon, right? Now in the next videos onwards, we will carry further this discussion to organic compounds. We will now introduce carbon in our organic domain, right? So I hope this video is clear. Now you know something about our member carbon. Further we'll continue in the next lectures. Thank you so much.